Hello friends, good morning. Myself C Patel and today I am going to discuss the GATE Metallurgy problem set 18. And in this problem set I have taken the theoretical questions from the grain refinement. Okay, so basically we will discuss the grain refinement in details and also do some theoretical problems here. Okay, so the first problem is why grain refinement is done. What is the reason for the grain refinement and why grain refinement is done? So grain refinement is done to enhance the mechanical properties of the metal. So the first is better strength. If the grain is smaller in size, then yield stress will be higher, so it will have better strength. Also it will have better toughness, better machinability, good surface finish. So these are the various different properties that is beneficial for the metal. So all these properties can be achieved by the grain refinement. So this is done. Now the second is, what is the effect of grain refinement on toughness of the material? Okay. So when we have large grains, suppose when we have large grains, so these are the large grains, so it will have a very low number of grain boundary. But if you decrease the grain size, a lot of grain boundary will appear here. So when we have large number of grain boundary and when the crack is initiated, then the crack gets an easy path to nucleate towards the grain boundary. So if the grain boundary is low in number, then the propagation of crack is very easy. So in that case, brittle fracture is easier. But if you decrease the grain size, it means that if you refine it, then the grain boundary becomes more and more, and in that case the crack propagation become more torturous. Okay, so because of the various grain boundary, the crack propagation is difficult, and in that case the brittle fracture is not easy. Okay, so that's the reason the toughness of the material is increased. So basically, if we increase the grain boundary by refining the grains, then the number of obstacles for the crack propagation increases, and that is the reason toughness of the material increases. Coming to the next problem. Do machinability increases on grain refinement? So machinability also increases on the grain refinement, because when the grain size is very fine or the grains are fine, grain size is very low, in that case the chips that is produced by metal working, that is machining, in that case if we machine the metal, then the chips or the flakes that we will get from the metal will be very small and small in size. So the surface finish will be better in that case. So the chip size of the machine metal is small, and if the grain size is large, then the chip sizes will be large, and in that case the surface finish will be not good. So machinability also increases on grain refinement, and if the chip sizes is large that is produced by the machining process, then it is difficult to machine. So this is also correct. Machinability increases on grain refinement. Now explain the microporosity. What is microporosity? So the microporosity comes because of the solidification of the liquid metal in the interdendrite region. So this is the dendrite, and this comes in the interdendrite regions. Whenever the liquid is solidifying the solid nucleates at the dendrite and at the interdendrite regions. If in the interdendrite region some liquid is left out, and this interdendrite region, the liquid is going to solidify at the last, and when the last liquid will solidify, because the solidification start from this end and goes on in this direction. So in that direction, if the liquid is trapped in the interdendrite region, then that liquid will solidify at last. And we know that if the solidification will occur, then the volume will decrease, because the volume of solid is less than that of liquid, and this decrease in volume will cause microporosity. Okay, so when the last liquid solidifies, it has shrinkage because the liquid occupies much higher volume than the solid, and this shrinkage occurs in interdendrite region, and this shrinkage is called microporosity. So this is the microporosity. Coming to the fifth one, explain the various methods of grain refinement given below. The first is RSP. RSP, the full form, if RSP is rapid solidification process, that is the RSP. And in this method we have high undercooling. Okay, so if the undercooling is high, then the nucleation rate will be higher, and a small critical nucleus will be formed in that case, and that will give you fine grain. So RSP is one of the very important method. In this case we do high undercooling, so the rate of undercooling is very high, like quenching. Okay, so in that case the nucleation or the critical nucleus size is very low, and we will get the fine grains. Next is mechanical vibration. Okay, in that case this is done in that way. If the solidification is taking place, okay, and the dendrite is growing, then we do mechanical vibration, and the mechanical vibration breaks the dendrite, that the growing dendrite will be broken down into a smaller pieces. Okay, and we get equiaxed fine grain by the breaking of this dendrite instead of columnar grains. That is columnar, if you don't do the mechanical vibration, you will get the columnar grain that is longer in size. But if you do the mechanical vibration, these dendrites will be broken down into equiaxed fine grains. Okay, so it is just the method of multiplying the grains by breaking the grains. Okay, and if we have the large casting, then this technique can't be used because its feasibility will be very low. So this mechanical vibration is generally used for a smaller casting. Now third is growth hindering agent. Growth hindering agent generally hinders the growth of the nuclei, and if the grain growth has been stopped or hindered, so it will result in a smaller grains or the fine grains. So we put some growth hindering agent in at the grain boundary, like in high steel, low alloy steel, that is HSL steel. We add some precipitate particles, and that precipitate particles pins the growing grain, and the grain growth is hindered. So grain growth hindering agent is added also to get the equiaxed or the fine grains. Coming to the fourth method, that is the cyclic heat treatment. In the cyclic heat treatment, we cool the steel sample. Okay, let's do it for the steel. We cool the steel sample from the austenite phase, that is gamma phase, to the temperature between, that is from gamma to temperature between A3 to A1. And in that case, the first pro-ectectoid ferrite come out of the gamma grains. So if this is the gamma grains, and if you cool it between A3 to A1, then some pro-ectectoid ferrite will come out. Pro-ectectoid ferrite will come out from this gamma grain. Pro-ectectoid ferrite will come out from this gamma grain due to this undercooling. Now again we heat this to austenitic range. Okay, so again these pro-ectectoid ferrites transform to gamma grains, but the pro-ectectoid ferrite that we get here is smaller, so the gamma grains that will be formed will be smaller in size, that is like that. Again we have to cool it from that temperature to between A3 and A1, and again new pro-ectectoid ferrite or even a smaller size will nucleate, and again we heat to get the same austenite phase. So this is done in various cycles, and at the end of each cycles the grain becomes more and more finer. So this is the cyclic heat treatment in which we get the finer grain size. Okay, the last is inoculation, and it is done in case of aluminum or iron based superalloys. And in inoculation, basically we use metallic particles, like in aluminum magnesium alloy we use the metallic alloy particle, that is MgAl2O4, that acts as a site for heterogeneous nucleation. Okay, in this AlMg alloy, and it promotes the heterogeneous nucleation and it leads to grain refinement. Some oxide is also used to promote the heterogeneous nucleation. So basically the main principle of inoculation is that it is done so that heterogeneous nucleation is promoted, and this heterogeneous nucleation leads to grain refinement, and this acts as a nucleating sites, that is the potent nucleating sites for aluminum grains where new grains are formed. So that's the end of this lecture. Thank you very much.